Hi, welcome to the lecture on Open Delta connection. From this video lecture, most of the doubts on Open Delta connection will get clear. That is how one of the transformer in Open Delta connection operates in 30 degrees lead and other transformer in 30 degrees lag. Open Delta connection is also called as VV connection and few others simply refers this as V connection. Open Delta connection is used where one of the transformer in delta-delta connected single phase 3 transformer bank gets failed. That is, if one of the transformer in delta-delta connection gets failed and where the continuity of supply is to be maintained, in that case open delta connection is used. That is, let's consider single phase 3 transformer bank which is delta-delta connected. Let the phase sequence be ABC. On primary side, the notations are in capital letters, and on secondary side, notations are in smaller case. So to have delta connection, we must join the finishing end of one coil with starting end of other coil. So here this is the finishing end. We must join this to starting end of this coil, and this is the finishing end of this coil, and which must be connected to starting end of other coil, and this is the finishing end, and this must be connected to starting end of other coil. So this is how we can obtain delta connection. Similarly, let's obtain delta connection on secondary side. So finishing end of one coil is connected to starting end of other coil. Okay, here this is the finishing end which is connected to starting end of other coil, and this is the finishing end which is connected to starting end of other coil. So this is how delta-delta connection is obtained for single phase 3 transformer bank. Open delta connection means if one of the transformer in this bank gets failed, then the resultant connection is called as open delta connection. Let's consider the transformer 1 got failed, and now let's observe the connection. Observe that here we are transferring 3-phase power which is having phase sequence ABC from one circuit to another circuit, that is from primary side to secondary side. Let us suppose that this transformer in this bank got failed. So now let's observe the resultant winding connections by removing this transformer from this bank. Now observe that after removing the transformer 1 from this bank, still we can maintain the 3-phase supply from primary side to secondary side. Okay, the same phase sequence A, B, C, and this resultant winding connection is called open delta connection. And I request you to keep this point in mind that when one of the transformer in delta-delta connected single phase 3 transformer bank gets failed, then obviously we think that there will be power interruption to the load. But with open delta connection, we can maintain the continuity of supply to the load, but with reduced capacity. To make the discussion simple, let's redraw the delta-delta connection in simple manner and observe the open delta connection. Let us suppose these three are the primary windings which are connected in delta, and the 3-phase power supply phase sequence is A, B, and C. And let us suppose these three are the secondary windings which are connected in delta, and now let's give the notations for the terminals of each winding. Okay, capital A1, capital A2, capital B1, capital B2, capital C1, and capital C2. And coming to secondary side, small a1, small a2, this is small b1, small b2, small c1, and small c2. Now we assume that one of the transformer in delta-delta connection got failed. Then we remove the transformer 1, means we must remove the transformer 1 primary winding and secondary winding from this delta-delta connection and observe the resultant winding connection. And the notations here A, C, and B. This is capital C2, this is capital C1, This is capital B2, this is capital B1. This is the winding which we removed. Similarly, let's draw the secondary winding connections. And let's mark the notations: small c2, small c1, small b2, small b1. And this is the winding which we removed. So when one of the transformer in delta-delta connected single phase 3 transformer band gets failed, then the resultant winding connection is called open delta connection. And with this open delta connection, we can maintain the continuity of supply to the load, but with reduced capacity. Now let's know the reduced capacity. That is, let's know the kVA rating of open delta connection. For that, let's mark the currents in secondary windings. Okay, so this is the secondary side line current ILA, this is ILB, and this is ILC. And the phase currents be IA to A1, I B to B1, and I C to C1. So when one of the transformer in delta-delta connection gets failed, what we assume, that transformer 1 got failed. So for that, we removed small a1, small a2 winding from secondary winding connections. So this is the resultant secondary winding connection. After removing the transformer 1 secondary winding from this delta connection, observe the currents in resultant winding connection. So observe that here, after removing the transformer 1 secondary winding, here this phase current directly passes through the line, means here IC to C1 is equal to ILA, means this phase current is equal to line current. In this case, IB to B1 is equal to minus ILB, and the magnitude is same, means here in this case also phase current is equal to line current. Therefore, by observing this, IC to C1 is equal to ILA and IB to B1 is equal to minus ILB. Therefore, from these relations, we can say that in open delta connection, line current is equal to phase current. And to avoid confusion, let's not discuss about ILC. Okay, ILC is equal to vector difference of currents IB to B1 minus IC to C1. Here in open delta connection, the phases present are only this winding and this winding, and the current flowing through these phases is called phase current, and these phase currents are flowing through the lines, means in open delta connection, line current is equal to phase current. Okay, please make a note of it. And it is known that the three-phase power for delta-delta connection is equal to root 3 VL IL, where VL is line voltage and IL is line current. And it is known that in delta connection, line voltage is equal to phase voltage. And coming to current, in delta connection, line current is equal to root 3 times phase current. Okay, let's replace these with phase values. And now this can be taken as equal to 3 into V phase into I phase. Therefore, this is the power delivered by delta-delta connection to the load. And now coming to open delta connection, it is known that the three-phase power delivered to the load is root 3 times VL into IL. But in open delta connection, here line current is equal to phase current. So replace line current with phase current and line voltage with phase voltage. So this is the power transmitted to the load by open delta connection. Now let's know the ratio of power delivered by open delta connection to the power delivered by delta delta connection. So kVA, power delivered by open delta connection, which is equal to root 3 times V phase into I phase, to the ratio of kVA delivered by delta delta connection, which is equal to 3 times V phase into I phase. So which is equal to 1 by root 3, and that is equal to 0.577. And now by rearranging this equation, we can observe that the power delivered by open delta connection is equal to 0.577 times the power delivered by delta delta connection. And what we generally think is that in delta delta connection, as there are 3 single phase transformers, so the power delivered by the delta delta connection is 3 times the rating of transformer. And now in open delta connection, as there are only 2 transformers, now the power delivered by the open delta connection we think is 2 times the rating of transformer, but that is wrong. The power delivered by open delta connection is 0.577 times the rating of delta delta connection, which is reduced capacity. Generally we think the power delivered by open delta connection will be 0.677 times the kVA rating of delta delta connection, but this is wrong. The power delivered by open delta connection is 0.577 times the kVA rating of delta delta connection. Okay, so this is the reduced capacity. Let's understand this with example. Okay, let us consider the rating of each transformer being 10 kVA, means the power delivered by delta delta connection is 30 kVA. And when one of the transformer gets failed, then what we generally think means the power delivered by open delta connection must be 20 kVA, because here 2 transformers involved. But this is not true. With open delta connection, the power transferred will be 0.577 times the rating of delta delta connection, that is 30 kVA. Therefore, with open delta connection, we can say that the power delivered to the load is 57.7% of the delta delta connection rating. Now let's know the utilization factor, which is equal to ratio of actual rating available to the sum of rating of transformers installed. Therefore, the actual rating available in open delta connection is root 3 times V phase into I phase to the sum of the rating of transformers installed. So the 2 transformers rating sum is 2 times V phase into I phase, and that will give you 0.866, means the utilization factor for open delta connection is 0.866, which will tell you that the power supplied by open delta connection is 0.866 times the installed capacity. And let's understand this with example. Okay, we consider each transformer rating is 10 kVA, and as in open delta connection there are 2 transformers installed, so the installed capacity will be, from the example, 20 kVA. That will give you 17.32 kVA. This value and this value is same. That is, if you want to find the power delivered to the load by open delta connection, means we can take 57.7% of the delta delta connection rating or 86.6% of the installed rating. That is, you can take kVA rating of open delta connection is equal to 0.866 times the installed capacity. So with this discussion, the point you must keep in mind here is that the utilization factor for open delta connection is 0.866, which is poor utilization factor when compared with Scott connection. Therefore, to have the three-phase power transmission with two transformers, we go for Scott connection because there we have better utilization factor, that is 0.92. Whereas in open delta connection, we have only 0.866 utilization factor. Now it's time to discuss how one of the transformer in open delta connection operates in lagging power factor and the other transformer operates on leading power factor. So to find the operating power factor, we just need the angle between this phase voltage and this phase current. Similarly, we need the power factor angle between this phase voltage and this phase current. That is, we need the power factor angle between VC2C1 and IC2C1, and similarly we need the power factor angle between VB2B1 and IB2B1. So if we can find the angle between this VC2C1 and IC2C1, we can find the operating power factor of this transformer. Similarly, if we can find the power factor angle between VB2B1 and IB2B1, then we can know the operating power factor of this transformer. For that, let's imagine this open delta connection is supplying power to the star connected inductive load. So let this be A1 dash and this and be B1 dash and this and be C1 dash and the neutral point be small n. So let's join the terminals like this. This is the star connected inductive load and the current flowing through these star connected loads are, this is ILA, same line current, and this is ILB, and in this load ILC. As the load is star connected, therefore the phasor diagram for this star connected load is, if suppose this is the VA1 dash phasor, and after 120 degrees in clockwise direction there will be VB1 dash phasor, and for further 120 degrees in clockwise direction there will be VC1 dash phasor. And here we consider the inductive loads, therefore the currents will be in lagging with the respective voltages. Therefore let the current be lagging by an angle phi. Okay, the current here is ILA, and similarly here the current is ILB, and here current is ILC, lagging by an angle phi. Now let's apply KVL to this loop CA dash N and C. That is KVL to loop C A1 dash N C1 dash and C, which implies that voltage here is V C2 C1 minus V A1 dash, and the voltage here is V C1 dash, but the current direction is opposite to what we are tracing, therefore plus sign V C1 dash equal to 0, which implies V C2 C1 is equal to V A1 dash minus V C1 dash, means the phase voltage V C2 C1 is equal to the phasor difference between V A1 dash minus V C1 dash. Okay, so this is the V A1 dash, and to have this voltage we need minus VC1 dash. So here this is the VC1 dash, and let's rotate this phasor 180 degrees. So this will give you minus VC1 dash, and the resultant of VA1 dash and minus VC1 dash is VC2C1, which is the required phase voltage of this transformer. And by symmetry, the angle between VA1 dash and VC1 dash is 60 degrees. Therefore, the angle between VA1 dash and VC2C1 is 30 degrees. And here in open delta connection, line current is equal to phase current. So ILA is equal to IC2C1. And to know the operating power factor of this transformer, we need the power factor angle between the corresponding voltage and the corresponding current of this transformer. Okay, here the corresponding voltage is VC2C1 and the corresponding phase current is IC2C1. Means the required angle is this, which is equal to 30 degrees minus 5. This is 30 degrees minus 5. Similarly, to find the operating power factor of this transformer, we need to know the power factor angle between this voltage and this current. For that, let's apply KVL to CB, B1, C1 dash and C. C, B, B1 dash, N, C1 dash and finally C. Here the corresponding voltage is V, B2, B1 minus V, B1 dash, and here the current direction is opposite to the tracing. Therefore, this is plus V C1 dash is equal to 0, which implies V B2 B1 is equal to V B1 dash minus V C1 dash. Therefore, this phase voltage is vector reference between V B1 dash and V C1 dash. Therefore, coming to the phasor diagram, this is the V B1 dash and this is the minus V C1 dash. So, resultant of V B1 dash and V C1 dash is V B2 B1. Therefore, the resultant of V B1 dash and minus V C1 dash is V B2 B1. And by symmetry, the angle between V B1 dash and V C1 dash is 60 degrees. Therefore, the angle between V B1 dash and the resultant is 30 degrees. And now what we need is the angle between V B2 B1 and I LB, that is I B2 B1. Therefore, now to know the operating power factor of this transformer, we need to know the angle between V B2 B1 and I LB. Okay, so this is the V B2 B1 and this is the I LB. Okay, and the angle between V B2 B1 and I LB is 30 degrees plus 5. Therefore, from this phasor diagram, we got the power factor angles of 30 degrees minus 5 and 30 degrees plus 5, which means that for lagging load, power factor of phi angle, one transformer operates at cos 30 minus 5 lagging, and other transformer operates at cos 30 plus 5 leading power factor. Therefore, for a lagging power factor angle of phi, the total power supplied by the open delta connection to the load is P is equal to kVA of one transformer into cos 30 minus phi plus kVA of other transformer into cos 30 plus phi. Therefore, for load power factor of unity, that is power factor angle is 0 degrees, then the total power supplied by open delta connection is kV rating of one transformer into cos 30 plus kVA rating of other transformer into cos 30, which means that for a load power factor of unity, both transformer in open delta connection operates at same power factor. Now consider for power factor angle phi is equal to 30 degrees. That implies the total power supplied by the open delta connection to the load is kVA rating of one transformer into cos 30 minus 30, 0 degrees. So cos 0 is 1 plus kVA rating of other transformer into cos 30 plus 30, 60 degrees, means cos 60 degrees is 1 by 2. So into 1 by 2, which implies that for a load power factor angle of 30 degrees, one transformer will supply its full rating and the other transformer will supply half of its rating. And similarly for load power factor angle of 60 degrees, the total power supplied by the open delta connection is kVA rating of one transformer into cos 30 minus 60 cos minus 30 degrees, and which is root 3 by 2 plus kVA rating of second transformer into cos 30 plus 60, means cos 90 degrees. Cos 90 degrees is 0, means this is 0. And from this you can note that for a load power factor angle of 60 degrees, one transformer will supply the entire load, whereas the other transformer will not supply any load. Now let's find out the ratio of kVA rating of open delta connection to the VA rating of each transformer. That is equal to kVA rating of open delta connection is root 3 times V phase into I phase, and the VA rating of each transformer is V phase into I phase. So that will give you root 3, which is equal to 1.732. And if you rearrange this equation, kVA rating of open delta connection is equal to 1.732 times the VA rating of each transformer, which means in open delta connection, each transformer is overloaded by 73.2%. And finally, following are the points that you must keep in mind regarding open delta connection. That is, the power delivered by open delta connection can be taken as equal to 57.7% of the total kVA rating, or you can take as equal to 86.6% of the installed capacity of open delta connection. And other than at load power factor of unity, the transformers in open delta connection operates at different power factors, whereas for a load power factor of unity, both transformers in open delta connection operates at same power factor, but one at leading power factor and other at lagging power factor. And in open delta connection, each transformer is overloaded by 73.2% of its rating. And coming to utilization factor of open delta connection, it is 0.866, which is poor when compared with the utilization factor of Scott connection. Okay, utilization factor of Scott connection is 0.92. Because of the Scott connection having good utilization factor, Scott connection is used to transfer three-phase power from one circuit to another circuit with the help of two transformers. This is about open delta connection.